So what can be more interesting in an ECE lecture than seeing a real program? Okay, so here is a program I typed last night to demonstrate the current homework and also the coming homework. So I divide the homework into, I divide this big program into two parts. So what you are going to see is that there will be one image. Okay, if you are here last time, you will see one image. This is the testing image. And then you will see two text files. Okay, so if you look at the command here, let me see if I can load it up. Okay, so if you look at the program here, you can see that there will be two data sets. They are both stored in the text.txt format. So you need to load these two, call it the training data sets. You need to read these two training data sets into your computer. And here the environment that I'm using is called a Google Colab. If you're new and talk to your classmates or go back to 2875 lecture notes, there should be materials telling you how to use this platform. As long as you have a Google account, you should be able to call this Colab environment. Then the way that I do to read these data is that I will map it to my Google Drive. So you can go to Google and just type, how do I map a Google Drive to my Google Colab? So you can find a command. I literally just copy and paste from the internet. So I mounted my Google Drive to this Colab environment. And then I called two libraries. One is the NumPy library. The other one is the matplotlib library. Again, you can find these information from the internet easily. I read the image. Okay, so this is my testing image. And then I also read the training data sets. In this case, the training data sets, they will be the two .txt files. One for the cat, one for the grass. I store them as two matrices on my computer. And so that would be, I don't know the dimension, but it has to be 64 dimension in one axis, and then the number of samples on the other axis. So it has to be 64 by something or something by 64. Okay, so that would be an array of numbers. So these numbers, so each number on in this array will represent a pixel value. So you look at one sample will be 64-dimensional vector. You can rearrange it to a by A patch. So each value will represent a pixel value on this patch. Okay, so these are your training sets. And then you can calculate the mean. So the command is np.mean, np.cov. Okay, so that cannot be easier. Now, of course, one advice here is that please look at the equation. Okay, you should be able to verify the equation according to this command. What I mean is that if you really type sum columns divide by 1 over n, literally type this up, np.sum, and then divided by something, you should be able to get the exact same result as what you're getting here using this command. If not, then there is something wrong with either the syntax here. Okay, the function has to be right. It's just that the syntax is wrong, or your implementation of this formula is wrong. So do a sanity check. Make sure that you understand what you're doing. And if you do it right, then you should be able to get something like this. So I just calculate the mean, calculate the covariance matrix. I also calculate the number of samples in my foreground, in my background. So they're different. Then you can get something like this. I just print the first two numbers of my mean vector. So you actually have these numbers. This is the number for the foreground. Okay, you should be able to plot 64 numbers. and here I'm just showing you two numbers to save the screen. Again, you should have 64 numbers. Here you should have a 64 by 64 matrix, although I'm just showing a 2 by 2, the first two corner. And then you have also this thing called a pi. Pi is just, if you read the instruction of the handout, you will see how I define the pi. Pi will just be the ratio between the number of samples for one class over the total number of samples. Okay, so you can calculate these. So if you do it right, you should be able to get all these numbers. And if you read the image, you display the image should look like this. Okay, so that's the first part. That should be pretty easy if you do it right. Although lots of many years, students they just mess up. They have something wrong with the syntax here and there. They couldn't get the 64-dimensional vector. They couldn't get the 64 by 64 covariance matrix, or they just dump in the entire data set into this command, and then they got a 9,000 by 9,000 matrix. They complain that they run out of memory, and then they just crop the first 64 by 64, and they say that it doesn't work. So all kinds of things can happen. So we want to make sure that you're okay on this part of the work. Now, if you're done, then we can start to do the inference or the testing. Okay. So part one will cover everything, including the training. Now, if someone asked me last time that, hey, it looks like there is no optimization involved. There's no stochastic gradient descent involved. I don't have a neural network. I don't have a loss function. I don't have anything. Where's the training? Well, the training in this case is embedded in this calculation of the mean and also the covariance matrix. Okay. In machine learning, there are two ways of doing a classification. One way is what you used to see. It's called the discriminative approach, where you build a classifier, and then you put up a loss function. Then you minimize all the parameters you minimize the loss function by finding the right parameter. Okay? Those are called the discriminative approach, where you really put in the classifier, you're discriminating your classification result directly. This is what the neural networks are doing today. Okay? The other approach, which is a little bit ancient, but it's called the generative approach. The generative approach says that I will start with a model, Gaussian distribution or Poisson or something. Okay, I start with a parametric model, and then my training is all about finding the model parameter. So in the Gaussian case, it means that I want to find the mean vector. I want to find the covariance matrix. If I find that, well, then the model is already defined, right? Then I can just build my classifier on top of that. What you're doing here is what we call the generative approach. We have a model, we have a parametric model here, we want to find the parameter. So once we find the mean, we find the covariance, we're done with the training. So during the inference, it will be the second half of the homework, not this week, but then the next homework. You need to write a testing procedure. Now you can see that the training procedure is fairly easy. Just if you do it right, it's fairly easy. Okay. Now the testing procedure will require you to loop it through the image. Okay. So you start with an image. You go through this image pixel one by one, doing this raster scan or horizontal vertical scan. You just do a double for loop. Okay. For I, for j, and then I will go with the column, j will go with the rows. So it's one pixel at a time. Okay. Now, smart students in this room will say, oh, how do I handle the boundary conditions? And the answer is ignore them. Okay. Don't worry about the boundary conditions. This is not a CS class that I'm going to be really obsessed about all these tiny little corner cases. I'm not. Okay. If you see the corner, ignore it. Okay. So if you don't have enough pixels, ignore it. Just go into the interior where you have pixel values. See my point? Okay. You don't have to worry about, oh, if I start with I equals to 0, how do I don't have pixels at my corner. Start with a place that you have a pixel. Okay. Eventually you get a smaller image, but you still see the pattern. Okay. All right. So now you do the double for loop. Then how do you actually run the inference code? It's as follows. And this is a little bit complicated, But anyway, okay, so here's the deal. You start with I equals to range n minus a and n minus a. So this sort of really defines the location, okay? Then you go to the image, this is y, and then you crop an 8 by 8. In our problem, it's 8 by 8, okay? So you crop an 8 by 8 patch, and then you reshape it. We reshape it into a 64 by 1 vector because this is what your training data set is doing. So you want to match the data. It will be a 64 by 1 vector, and then you dump it into a thing like this. Okay, you calculate the inner product. There's a covariance matrix inverse Gaussian, right? Gaussian distribution. So you look at the Gaussian formula. This is really the Gaussian formula. Just plug it in. Okay, so calculate that. Then you compute the probability, the density values, and then you see which one's higher. Okay, see which one's higher. If the cat probability is higher than the grass probability, then your output here I define an array called a predict. You put a 1 there. Otherwise you put a 0 there. Okay, so it's really writing this double for loop, calculating the probability, and then messing things up, and then cry for a couple hours, and come to me, and then fix the bug, and then you get a number. All right, so is that process. Now, if you do it right, okay, so let me just click the button. It will take a while, okay? Really a while. Let's see. So if you haven't got any experience in terms of machine learning or training or something like that, testing, this is, in my timeline, this is called instantaneous. All right, why? Because the scale that I have will be 7 days on a GPU machine on the supercomputer center. So this is the time scale that I have, okay? So if you get the result here, it's called instantaneous. All right, so now if you feel that this is too slow, okay, it's actually okay. It's actually okay. Now, you need to think about how to make this not too crazily slow, okay? So here's a hint. If you implement this according to the formula, you really calculate NP dot exponential something, and then inverse and something like that, that will really take you a while. And that a while means in the order of minutes, okay? In the order of minutes per image. Now, clearly you see in this demo is in the order of seconds, okay? So I did something. I did something to make it faster, from the order of minutes down to the order of seconds. So that is something that you need to think about. But overall speaking, this kind of program is still, I call it fast, okay, compared to a visual transformer that you need to train for a couple days on A100. So this is pretty easy. Okay, so now if you do it right, the image should look like this. Okay, it should look like this. You may have some variations here and there with some bugs here and there, but it should look like this. So if you get something totally off, that's not the problem set up, it's your problem. Okay, I'm telling you the answer. There's no ambiguity. You should be able to get something like this. If you're not getting it, it's your problem. Now, I forget if I have another open question asking to make it better. Okay, I forget if I have something like this. Make it better. So basically, I ask that you should. It's an open-ended question. Now you see some false alarms at the floor. We see that false alarm at the floor, and then some myths at the head of the cat. So can you fix those? Can you fix those? One answer that will no longer be accepted, okay, starting from this year, is that you cannot manually crop the cat and say that pixels outside cannot be used. Okay, so you know what happened in the previous years? Students, they're so smart. They're so good in Photoshop. They take this mask, they draw a boundary They say that anything outside can be ignored. It's called the post-processing step. Some are smarter. They say, oh, according to human visual system, pixels in the center is most important, and therefore I draw a bounding box, and anything outside the bounding box, I'm going to ignore it. Okay. So number one, I'm not a big fan of human visual system, that kind of crap. Okay. So I don't do that kind of research. I really want you to think about in this image, what are the features? Okay. Don't use this kind of cheating things to cheat me. Look at this image. What are the things that you can really do to make this decision a little bit better? I'm not asking you to reinvent the neural network or whatever. Okay, I'm just asking you to think about the image character, think about the problem you have, and see if you have any suggestions to make it better, and you can implement something. And in the past, there are really good students. They implement a shallow network. They know the technique. I'm not asking you to do it if you are new to neural networks. So some students, they did try neural networks and they say, well, the performance is comparable or slightly better. And sometimes they say it's worse. So that would be a good finding. Okay, I'm not asking for, oh, it got to be 3% improvement. No, I'm not asking for that. It can be worse. And just tell me why it becomes worse. It's okay. It's okay, right? So try that. Have some creativity here. Don't do the dumb thing. Okay. If you're lazy, I can tell you're lazy. It's very easy to tell. Okay. So it's more a thing to test how much effort you want to put into this process. I think it is very fun. Okay. I think it really connects a lot of things that we have been learning in this class. So I encourage you to work on it. Questions so far? Yes. Mm-hmm. Correct. Is it all on the photo data, or do you also use the testing entry? So this week's assignment, you just need to do the training. Basically, type these codes. Okay, you just do the training and make sure that your covariance matrix, your mean vectors, they're correct. Okay. Next week's assignment, also through the Thanksgiving weekend, you're going to write the longer one, the testing procedure, the double for loop. Okay. Don't download an image from the internet and test it. It doesn't work. I promise. It won't work. I've been cheating too much on this assignment because the training set comes from the testing set. I know I'm detouring, but I will still tell you, if you want to do machine learning later on in your career, don't do this kind of cheating. Make sure that your training and your testing, they're put aside. Okay, never touch your testing data set when you do the training. Really, put it in a lock. Okay, put it in a safe. Don't touch the testing set. Nowadays, when you look at a lot of these conference papers, they want to beat the state of the art. So they fine-tune the algorithm by looking at the testing data set. Now, of course, you can beat the state of the art because you're cheating. You're looking at the testing data set. And sometimes it is unintentional. Okay, you just look at the results. You look at, oh, it doesn't work. So I start to tune my algorithm. And because you tune your algorithm with respect to the target data set, you are really not asking the network to generalize. So the trouble is that I'm not going to deduct your points. You're not satisfying me. The downside is that later on, when you deploy your system onto an unseen situation, you are going to suffer a lot. That's the problem. Okay. So if you fine-tune too much towards one scenario, you're going to suffer on the untuned scenarios. So as you are training your network, you're training your classifiers, make sure that it has enough generalization capability. That's very important. Okay, cool. let's go back to our thing, multidimensional Gaussian. So I want to spend a little bit of time talking about some pictures of this multidimensional Gaussian. Again, this lecture will not be tested in exam. Okay, we have enough to test you. You just had a wonderful strike back test. So happy? Yeah, happy. Okay, great. There are too much unhappiness in life, so you want to get something happy, right? So that's the most important thing. Okay, so I'm not going to test you in the exam, but I think it's very important to know the picture, okay? Because this high-dimensional Gaussian is just so useful. Okay, so to start with, there is a vector. You have the covariance matrix. Covariance matrix is given by this formula, okay? So now let's look at this joint Gaussian distribution, a high-dimensional Gaussian distribution. It has this form. It has this form. This form is nothing crazy. You have a mean vector, and then you have your state. Now the state becomes a vector, and then you have this covariance matrix. You take the inverse. You have the determinant. You have this dd is the dimensionality of the vector. So we have seen this formula before. What I want to do today is to talk about the shape of this Gaussian matrix. So this is the this is sort of the one special case where your x is independent. So when your x is independent, your covariance matrix becomes a diagonal matrix, and so you can invert it. You get back the summation of the individual cases. So it will just become the multiplication of individual Gaussian, one-dimensional Gaussians, because it's a sum in the exponential, right? So you look at this. This is if you put exp of minus sum of xi minus mu I squared divided by 2 sigma I squared, I going from 1 to d. This is really just the product of multiple exponential functions, okay? So this is the independent case, the easier case. Now, what if they are independent? Then, well, the PDF becomes this product of individual one-dimensional Gaussians. So that will make your life a lot easier. Anyway, so let's look at the shape. I mentioned that last time. The shape of a Gaussian is dependent on not the mean vector. The mean vector will only tell you the location, the center location of the Gaussian. The shape, the orientation, and also the elongation of this ellipse is defined by the covariance matrix. So I want to talk about how this is defined. On MATLAB or Python, you can plot the scatter plot using this command called the mbnrnd. So there's an equivalent in Python. You can also plot the scatter plot. If you want to look at the command, you can go to the book. The book will have all these commands ready. In fact, if you go to the website for the book, you have Python, MATLAB, R, and Julia, your 4 languages, okay, for plotting these things. Another plot, so this is about plotting the contours, okay? So to plot the contours, what people do in computer is that they define a mesh grid, and then on this grid they evaluate the points and they connect the dots. So so that you can do it in computer. Okay, so I want to talk about something that you haven't learned before. Okay, how many of you have learned Eigen Decomposition? 1, 2, at most. Okay. In order to analyze this orientation of the Gaussian, okay, in order to analyze the orientation of this Gaussian, we need to look at the covariance matrix. The covariance matrix in a 2-dimensional case, it will have 4 numbers. It will be the variance of x1, covariance of x1, x2, covariance of x1, x2, and then the variance of x2. Okay, so if these 4 numbers, it will be a 2 by 2 array. Okay, so this is a matrix. Now the way to analyze this matrix has to be done through a technique called the Eigen Decomposition. So to summarize this Eigen Decomposition is a decomposition of a matrix. So you start with a sigma. So this is a 2 by 2 matrix. You are going to decompose it into 2 matrices. It will be U and S. Okay, it will become a U and S. And let me make sure that I have this transpose on the right place. Okay, so you are going to write this sigma. It will be equal to U as U transpose. So this is what we call a decomposition. I haven't explained what that means, okay? But it will be a decomposition of a 2 by 2 matrix into a product of 3 matrices. Okay, at this moment you will be like, what the heck, okay? You have, this 2 by 2 is complicated enough. Now you want to write it into a product of 3 matrices. They're all 2 by 2. Why are you wasting so much time here doing these? Okay, so here's the beauty. There are properties for these 3 matrices. They're not arbitrary, okay? Especially for the matrix in the middle, it will be a diagonal matrix. So it will be S1 and S2. There will be 0 on the 2 diagonals. It will be a diagonal matrix. Now, these 2 matrices, they are not arbitrary either. These 2 matrices, they will have 2 column vectors. In this case, you will have 2 row vectors. Okay? So you have 2 column vectors and 2 row vectors. These vectors, they have the property called orthogonal. It means that if I take the first column vector, I take the dot product with the second column vector, I will get 0. So they are orthogonal, they're perpendicular to each other. Okay? So how do you do this process? Well, this is not the purpose of this class. It will be the purpose of a linear algebra class. So let me tell you how do we do it. The answer to do this decomposition is EIG in MATLAB or NP.EIG in Python. Okay. So someone who knows this thing is laughing at me. What the hell is this professor teaching? Okay, so he's really not teaching math, he's teaching the command. Yeah, I'm teaching the command because to teach this math, it will take forever if you're not in a linear algebra class. So what we're doing here is that I'm going to give you this covariance matrix. It's a 2 by 2 matrix. And in fact, it can be any dimensional matrix. It can be 64 by 64. You can run this command called the Eigen Decomposition. MATLAB or Python is going to produce you this pair of matrices. The U matrix that contains 2 columns, and then the S matrix that contains the 2 entries in this diagonal matrix. It's going to give you that. So you will have this U matrix, this S matrix, and if you don't believe me, you can try your MATLAB and Python. You can decompose it, and then you can do this multiplication. And if you do it right, you should be able to get back your sigma. You should. If you do not, then there's something wrong on you, not on me. Okay, not the math. Math will never lie. Okay, it got to be something wrong with your code. So if you do it right, you should be able to get this decomposition. Now, there's some very beautiful properties about this covariance matrix, this decomposition here. So what are they? Well, before I do that, I will just quickly scan through these slides. So how do we determine the shape of Gaussian? By the Eigen Decomposition. So that's a definition of the Eigen Decomposition. And before that, there's a definition of eigenvector. An eigenvector is a vector, a U, that when you multiply your matrix A with this U, it's going to give you this U back with a multiplier called the lambda. It's called the eigenvalue. Okay. So what is this thing? Think about there's a black box. There's a black box. Okay. This black box is going to eat something, right? So whenever you think about a black box, okay, it's going to eat something. So it's a function. You eat something and it returns you something. So if this black box is defined by this a matrix called an A matrix, basically you give me an input vector. I give you the output vector of A times your input vector. Right? So this is called a linear system. Now, there is a very interesting property of this eigenvector. It is a very special vector that you input this U through this system. Well, the output should be A times U. But because this is so special, it will return you a scalar times the input. So it's like a characteristic of the system, because this special vector u is uniquely defined by your system matrix. You have a different A matrix, I will have a different very special vector u. So if you're taking 301, do you know what is a Fourier basis? Okay, E, J, omega. Do you know what that is? This is called the Eigen basis for your time invariant system. Okay, as long as you have a time invariant system, you send in this thing, you will get back this thing with a scalar multiple. That's called the Eigen Decomposition. Okay, that's also called the Fourier Series. So what is a Fourier Series? You have this cosine sine function, you decompose it into many sine functions, and then you send this in. It has to come out unchanged, the frequency. Okay, you send the frequency in. If this is linear time invariant system, a sine function goes in, has to come out as a sine function. The frequency will not be changed. Okay, it's just that you were going to multiply, you amplify or attenuate the function. Okay, that's why the Fourier series is so special. It is the orthogonal decomposition of your linear time invariant system. Okay, so that would buy you a lot of things, because what is going on here? This Eigen decomposition. What are these S matrices in your Fourier system? This would be your Fourier spectrum. This is your frequency component. These will be your frequency basis, sine basis, cosine basis. Okay, so these will return you the Fourier coefficients. Okay, so it's like it's very powerful decomposition. All right, so now this is the definition. Anyway, we just need to know that if I have this A matrix or sigma matrix, I can decompose it into this form. You have a column matrix, you have a diagonal matrix, and row matrix. You can write in this form. In Python MATLAB, it's very easy. Eig, and then diagonal to pull the numbers. Okay, very simple. Oh, by the way, you need to make sure before you do anything, make sure that your A matrix is symmetric. Okay, because I'm talking about the covariance matrix is a symmetric matrix, so everything will work. If you just arbitrarily dump in a random matrix, you're going to get imaginary numbers, because for this Eigen decomposition to work on real numbers, it got to be symmetric. That's a property. So if you arbitrarily dump in a 2x2 matrix to MATLAB Python, it will complain. They will say that it is not a symmetric matrix. They will yell at you. Okay. Another thing they will yell at you is that all your lambdas has to be positive, and this can be proved. If I start with a covariance matrix, these numbers has to be positive. So again, if you arbitrarily dump in a 2x2 matrix into MATLAB and ask it to plot a Gaussian distribution, it will yell at you because there's no guarantee that these are positive numbers. Okay, so you need to construct your covariance matrix appropriately. So long story short, let's go to the picture. Now you have two things. One would be the column vectors. Two would be the diagonal entries. Okay, very important. There are two different things. It turns out that your vector would define the major and the minor axis of your Gaussian. Okay, so you look at this column vector. This column vector, a vector, of course, would point you from the origin, 0, 0, to your point, right? So this would be, let's say, two numbers. So that would be a coordinate. So that you can connect the origin and then the coordinate, that gives you a vector. So that will define you a vector along one direction. That would be a major axis. And then you have another vector, so that will give you a minor axis. So you have these two vectors. Okay? Direction, just the direction. Okay? The starting point is defined by the mean vector. So I can start with this point, I can start with this point. It depends on where my mean is. So that would be the direction, major axis, minor axis. And then I have the magnitude. How long is my ellipse? How tall is my ellipse? How short is my ellipse? That is defined by lambda 1 and lambda 2. Okay, so now you look at a 2x2 matrix, you say, okay, what should be the orientation and how big and how small it is? do this eigen decomposition, then you can plot it out. You can see how big and how small it is. And therefore, if you look at this example here, again, you can see that why this is 5.5. Well, because this is 5, this is 0.5. Okay? And the two eigen matrices, they are just orthogonal vectors. One is pointing to the right, one is pointing to the up. Here, when you have this matrix, you can prove by using the eigen decomposition that one is pointing here, one is pointing there. So it seems like things here. Okay. Now whether this is pointing up and down doesn't matter because you have a pair. You have one on the left, one on the right, so you will take the square anyway, so it doesn't matter. Here are some examples. If I take the eigen decomposition, I will get the two vectors. So you can see that this is 0, 1, 1, 0. So orthogonal, perpendicular, one horizontal axis, one vertical axis. These are the two numbers. Okay. This one is minus 0.7. So it will be minus 0.7, minus 0.7. So it will be pointing to this direction. And then minus 0.7 and plus 0.7, you're pointing to this direction. Again, they're perpendicular to each other. So the third case is similar. Okay, so will you get negative eigenvalues? You will never get negative eigenvalues. You will never. If you ever get a negative eigenvalues for the covariance matrix, you're wrong. Okay, so this sort of summarizes this Gaussian PDF. Okay, so now I want to talk about something, not this lecture. This one you can learn it later in the other course, but I want to talk about this. This is also very useful. Principal component analysis. How many of you have heard of this term? 1, 2, 3, 4. Okay, a couple of you. Okay, PCA. So how does this work? If you don't know PCA, let me tell you. PCA is a very powerful thing. I have measurements. I want to find out its representation. I want to find out its best representation. I don't want to store my phase image. I only want to use a few coefficients to store it. How do we do it? PCA, okay? Principal component analysis. What is this? It is the eigen decomposition of the covariance matrix sigma. So here's the deal. You start with a data set. You start with a data set that contains many, many, many columns, okay? Column vectors. They are the samples. You calculate the covariance matrix. Calculate the covariance matrix, and then you run the eigen decomposition. Get the eigen matrix, eigenvectors, and eigenvalues. The eigenvectors, they are the principal components. That's it, period. Okay? It's very simple, okay? So if you ever read online notes, they confuse you a lot. That's not the goal. It's very simple. So let me see how, I want to skip the equations because it doesn't make sense to flood you with the equations since we're not going to test you. So here's a demonstration. Very, very classical problem. It's called the Eigenface problem. Eigenface problem. You have a data set that contains a lot of these faces. I forget the dimension of these faces. But you can always reshape them into column vectors. So each image, it will be an n by n matrix. You can make it into a long column vector by np.reshape. Okay, you can do that. So you have all these vectors. Each vector represents a d by d image. And now I want to find a low-dimensional representation. What do I mean by low-dimensional representation? I don't want to remember all these pixel values because in order to remember these pixel values, I have d pixels to remember. It will be a long vector to remember, and everyone's different. Now, however, if I look at the images, okay, if I look at the images, here is a face, human face, okay? So now I can represent it as a column vector. This image can, in fact, be represented as a linear combination, meaning that you have all these column vectors. They're the basis vectors, or they're the eigenvectors that you can compute from np.eigen. or in MATLAB just EIG. You can compute them, and you store them as these column vectors. Okay, so these are pre-computed. You have access to them before you do anything. Okay, you have already trained your covariance matrix. You can do this thing beforehand. You get all these U1 to UP, and then for different image, you just use a different combination of these coefficients, alphas. So alphas would be different for different image. Now you look at this gentleman here. He has alpha 1 to alpha p, will be 1 and 2 and 1.2 or 2.5, some numbers for these alphas. If I change this picture to another person, these alphas will change. However, the U's will not change. The U's will not change. Okay? So what I mean is that originally, I need to represent this image using D variables, right? D numbers, D pixel values for this image. And that could be, let's say 64 by 64, you already get a pretty large number of pixels. And here, let's say I only have 100 bases. Then to represent this human face, you just need 100 coefficients to represent this human face. Okay, so there's a huge dimensionality reduction going from let's say 1 million pixels, okay, down to just 100 coefficients. Now, where does the saving come from? Well, the saving comes from the fact that all these U's, they are predetermined. The U's are already given to you. They're the basis functions. They already know. What you need is to find out the coefficients. Okay, and so this Eigenface problem, or PCA, is all about finding the basis functions U, which in my language is Eigen Decomposition of covariance matrix. That's it. Okay, and then the next step is how do you use it? To use it is that if I can find out the alphas, then I can just make any kinds of decision based on the alphas. So think about the following situation. You have a face. You want to determine whether this gentleman belongs to class 1 or class 2. Okay? Originally, what you would do, using the project that we have here, you take the entire column, you look at the pixel values, and then you build a classifier on these pixel values. Huge dimensionality problem. And now, because all these faces can be represented by these coefficients, I just need to train a classifier based on these 100 coefficients. Okay? I will still have 10,000 of these face examples, but each example can now be represented by a 100-dimensional vector instead of a million-dimensional pixel array. So that would be a dimensionality reduction. So then you ask, how do we calculate the alphas? Well, calculating the alpha is actually very easy. Very easy. So here is your vector x. Here's your vector x. Here is your basis u1 through up. Okay? Alpha 1 will just be u1 transpose xn. Now, this n denotes the nth training sample in your data sets. So n will run from 1, 2, 3 to 10,000 training samples. So this is the small n. Each one will be a vector x. If you take the inner product of u and your x, you'll get an alpha. Now I'm skipping the derivation here. Basically, the argument is that your U matrix is orthogonal, and therefore, by doing this operation, we call it projection operation, you can get the coefficient. So the story is complete, right? Because you give me the data sets, I run the Eigen Decomposition, I find you the basis vectors, and then now you hand in a new image to me. I calculate this projection. Basically, I find out the alphas, and then based on the alphas, I run my classifier. Okay? So the PCA is what? The PCA is the process of going from the data set to these basis functions. Okay, so let me see. I don't think I have another slide showing you how to do this on the computer. But never mind. This one could be useful in case you know something about PCA. PCA is what? PCA is a tool for dimensionality reduction. PCA is nothing magical or something like that, okay? And don't feel that, oh, I have this word PCA, so my report becomes a lot more fancier. No, 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 no. It's not like that, okay? Sometimes undergraduate students will feel like by putting more of these hot, sexy words in your report will become a lot more valuable. The truth is that is usually it has negative impacts on your report if you don't know what you're talking about. Okay, so what is PCA? PCA is a dimensionality reduction tool that can help you go from a very, very big high dimensional vector to a small dimensional vector. And then you can do the decision over there. So that is the process of PCA. And then now there's some limitation of this PCA. There are data sets that your PCA doesn't work. So let's say your data is distributed in this way. Then you can easily find one major axis and then the other axis. So this PCA idea will work. They can pick up the different orientations. So that will work. Now, if a data set is distributed in this way, then it doesn't work. So some students think that, oh, wow, I have a data set. Let's run PCA, and then let's get the components. And then they plug it into the classifier, and suddenly it doesn't work. They say, how come it doesn't work? I say, look at your distribution data set. It could be like this. The PCA is not helping you. Okay. I have been using PCA quite a while. They're very useful. So for problems like imaging through long-range turbulence, then you want to capture different types of blurs. Now, if you want to model each blur one by one, it will take you forever because the blur just changes every second. So, but then if you have this PCA built in, you only have 100 bases. Then you just need to learn the coefficients of each measurement. So that will save you a lot more. In terms of storage, in terms of computation, it also saves you the estimation because the inverse problem will be a lot easier. The inverse problem, originally you want to find out the entire blur. Now you just need to find 100 coefficients. So the estimation problem becomes easier too. Okay? All right, so I will stop at this point. And then when we come back, I will move on to chapter 6. So please download the slides, and then we will talk about something that will show up in the exam. Okay, so I'll see you next time.